In geology, the transition from chaotic, boiling liquid to solid is a transition into mathematical order. Out of violence, matter locks into precise geometric structures. To understand these structures, we have to start with a strict definition. A mineral is a naturally occurring, homogeneous solid with a definite chemical composition and a highly ordered atomic arrangement. A definite chemical composition does not mean the formula is permanently fixed. Take olivine, seen here as these green clusters inside volcanic rock. In its structure, magnesium and iron atoms share the same physical size and charge, meaning they easily substitute for one another. The composition can swing from pure magnesium to pure iron, but the atomic framework holds. Traditionally, this definition excluded organic processes, but modern mineralogy accounts for biological constructs, like the rigid carbonate lattices built by marine organisms for their shells. Regardless of its formation, the defining characteristic of any mineral is that highly ordered atomic arrangement. The macroscopic boundaries of a solid object are entirely dictated by an invisible, microscopic grid. Without physical impediments to growth, the internal grid manifests externally. This clear quartz cluster demonstrates the result: a symmetric solid with perfectly flat faces. Every flat face is a rigid physical boundary dictated by the mathematical laws of internal symmetry. Perfect crystals are rare. In nature, minerals compete for space and resources. They grow crowded, warped, and lopsided. But the mathematical rules governing their growth never break. In 1669, Nicholas Steno proved this. Look at these three cross-sections of quartz. One is perfectly formed, and two are highly distorted. Yet, if we measure the angles between corresponding crystal faces, they remain exactly 120 degrees across all three specimens. Steno's law holds true because the macroscopic shape is building upon a repeating three-dimensional network of atoms, known as a lattice. The exterior can warp, but the internal lattice remains perfectly invariant. To study this invariant structure, crystallographers rely on symmetry operations. A symmetry operation is any physical or mathematical maneuver you apply to an object that results in zero change to its external appearance. By testing which operations leave a mineral looking identical to its starting position, we can map its internal atomic architecture. Every mineral on Earth is built by stacking just three exact physical operations: rotation, reflection, and inversion. The first structural tool is rotational symmetry. This is an imaginary axis passing through an object, around which the shape repeats its appearance multiple times during a single 360-degree spin. Consider this square 2D lattice. If we rotate it exactly 90 degrees, the orientation of the atoms matches the starting state. It achieves this identical appearance 4 times within a full circle. Therefore, it possesses a fourfold rotation axis. Along with fourfold axes, mineral lattices frequently utilize twofold rotation, repeating every 180 degrees, threefold, repeating every 120, and sixfold, repeating every 60 degrees. However, objects in the macroscopic world frequently exhibit fivefold, sevenfold, or eightfold symmetry. Why do we never see these specific rotations in the atomic structure of crystals? The answer lies in the geometric requirement of the lattice. Atoms must perfectly pack together to fill three-dimensional space without leaving gaps. If you attempt to tile fivefold pentagons or eightfold octagons, the geometry fails. It leaves massive, unfillable gaps in the structure. A microscopic spatial budget rigorously restricts nature's macroscopic beauty. If the atomic geometry cannot tile perfectly, the structure simply cannot form. The second geometric operation is mirror symmetry, or reflection. This requires an imaginary plane slicing through the object, where one half acts as a perfect reflection of the other. Slicing a rectangle vertically and reflecting half across that plane recreates the original shape, a valid mirror plane. But consider a diagonal slice. Mirroring the bottom half across that cut breaks the geometry, creating a jagged polygon that fails the test of invariance. Therefore, the rule of invariance is absolute. If a mathematical operation generates a new macroscopic shape, it is not a valid element of that crystal symmetry. The final foundational operation is the most abstract: inversion through a center of symmetry. denoted mathematically by the letter I. To test for inversion, we draw a line from every point on a crystal's face, passing directly through a single central coordinate inside the crystal. Extending these lines an equidistant length to the opposite side projects a perfectly inverted, upside-down replica of the face. By compounding these base actions, complexity scales up. A prime example is rotoinversion, a sequence where an object is first rotated and then instantly inverted through the center point. Take a standard cube. If we apply threefold rotoinversion, we rotate the top faces 120 degrees along a corner axis, and then those faces are projected straight through the center to generate the upside-down bottom faces of the cube. Rotation, reflection, and inversion form the complete crystallographic toolkit. Every geometric variety of mineral found in the Earth's crust is constructed by combining these three variables. In nature, these symmetry operations never exist in a vacuum. When you combine them in three-dimensional space, they act upon each other. They multiply, stack, and mathematically force other symmetry elements into existence. Let's build a complete mineral class from scratch. We start with a solid, featuring tall rectangular sides and a perfect square top. Because the top is a square, the geometry requires a primary four-fold rotation axis, running vertically right through the core. The rectangular side faces dictate their own rule. They require a horizontal two-fold axis, passing through their centers. Now the emergent math takes over. When you execute the 90-degree turn required by the vertical axis, it physically moves the horizontal axis to a new position. To satisfy the rule of invariance, a second perpendicular two-fold axis must inherently exist to cut through the front and back faces. The chain reaction continues. The interaction between the square top and that four-fold rotation forces another set of two-fold axes, cutting diagonally right through the corners of the crystal. We must also account for reflection. The layout of the square top and rectangular sides guarantees corresponding mirror planes, cutting vertically across the faces and down the diagonals. Finally, a horizontal mirror plane slices straight through the equator. Because of the sheer density of these intersecting planes and axes, this crystal inherently possesses a central point of inversion. From a single square top and rectangular sides, the laws of geometry generated one four-fold axis, four separate two-fold axes, 5 distinct mirror planes, and a center of symmetry. This specific combination of operations forms class 4 over m, 2 over m, 2 over m, known as the ditetragonal dipyramidal class. It is one of exactly 32 possible symmetry combinations that can mathematically exist in three-dimensional space without leaving spatial gaps. Every mineral is a physical manifestation of strict, unbreakable geometric law, a solid proof of the invisible mathematics